today is class number 3 and we are going to discuss Bus Admittance Matrix. So we are now entering into load flow. So the first module is load flow. In power system operation and control, the first module is load flow. Okay. So last two classes what we discussed is the background, which was already covered in power transmission. Okay, like the complex power and the transmission capacity. That was the background. So today we are starting with the module 1 or the CO1, where you should at the end of this module you should know how to compute load flow or power flow. As I told you, load flow is a steady state problem. That means the load flow that you will see is a snapshot of the system. At current time, how much power is going through what lines. So this is basically a network theory problem. Okay, and as you know, we can find out current by means of voltage divided by impedance or voltage into admittance. Okay, so because of certain benefits, the admittance method is used in power system operation and control. Okay. Okay, so we will start with bus admittance matrix. So power flow studies. So power flow studies are basically steady state analysis of an interconnected power system during normal operation. The first line you should write. Okay, it is a steady state problem. Load flow is a steady state problem of an interconnected power system during normal operation. No faults. Okay, no faults, no dynamic conditions. Only steady state load state. In fact, this is a snapshot at a particular instant when load is fixed. The system is assumed to be operating under balanced condition and represented by a single phase network. So as I told you, if we want to do a single phase analysis for a three phase system, the requirement is that, what is the requirement? It should be a balanced system. Okay. If it is a balanced system means load and source, these are balanced. Okay. Current is equally divided in all the three phases. So it's a balanced system, 120 degree apart. So if it is a balanced system meaning what? The voltage and current phasors in each phase are separated by 120 degree phase angle. 0, minus 120, minus 240 or plus 120. So that is the balance system. Okay. Network consists of hundreds of nodes and branches with impedances specified in per unit on a common area base. So when you take the whole country as single grid, you have thousands of nodes. Even the state of Odisha has many nodes. Okay, node means it can be a load, okay, or it can be a generating node. For example, you have a power plant when it is generating power to a transformer plant, so it is a generating node. Okay, NTPC, they are captive power plant, or some Hindalco's captive power plant is a generating node, also a load node. Okay, so what we are going to use? We are going to use node voltage method. So you have known several methods in circuit theory. Node voltage method means V minus V1 minus V2 by J or V1 minus V2 by into Y. And if we take a reference ground node, then the current is V minus 0 by the impedance. Okay, that method we are going to use. Formulation of network equations in nodal admittance form. So we are going to use nodal admittance form, not the impedance form. Why? It will be clear at the end of the slide. Now, what is important to know is that load flow equations are algebraic equations. Now, can someone tell me why it is not a differential equation? Why it is algebraic equation? Load flow equation. The answer lies in the slide itself.
Because it's a steady state.
Because it's a steady state, there is no time change. Okay, d by dt is 0. There is no time change. So that's why it is a algebraic equation. But it is a complex equation. Why it is a complex equation? Phasors. Real power and reactive power. Both are. That's why it is a complex equation. Okay. Next, power are known rather than currents, hence the term power flow. So we are bothered about the power. What is generated, what is consumed. Current is just a means to transfer power. We are not bothered about the current. as far as our end objectives are concerned. So these are known as power flow, more specifically load flow equations, because our objective is to send power to the load buses. Okay, that is what matters. Power flow analysis studies commonly referred to as load flow are the backbone of power system analysis and design. So anything that you want to do in future, a new power system installation or new power plant installation, first you have to do a power flow on a steady state system. Okay. So it's mostly a planning problem. Okay. So this part I have taken from the Hadi Sadar book. Okay. You can refer to any book. It's a simple concept. So we'll start with developing the bus admittance matrix. So draw this network. This is a network having how many buses? In power system PSOC, you are going to see this type of diagram where this single line is known as a bus. Okay. This is a kind of generating bus because there is a generator connected to it. Okay. This is another generating bus, a generator connected to it. Okay. And there are no nodes shown here. Okay. Simple impedance diagram is given. Impedance diagram means all the elements are replaced by their inherent or internal impedances. For example, this is the generator reactance. J1 is the generator reactance, J.8 is generator 2 reactance in parity. In PSOC, we use only parity. Okay, we are not bothered about the exact value, and unless it is a fault condition. Okay. So these are the admittance, the impedance of the transmission lines. Note that resistance is neglected. When we neglect resistance, we are actually doing a conservative analysis. Okay. Okay. Because in resistance there will be losses. Okay. So resistance is very small compared to the reactances, and we neglect that in power conversion. So these are the impedances. These 1, 2, 3, 4 are the buses. These are the line impedances, and these are the generator internal impedances. So this is the impedance diagram. In power flow analysis, we convert this to a admittance diagram. So what is the admittance in this case? 1 by J1, which is minus J. 1 by J.8, which is 1.25 J, minus 1.25 J. Accordingly, all this. So the next step is the admittance diagram. Draw it. So in step 2, we do the admittance diagram, where generator, as you know, from impedance equivalent circuit. What is the equivalent circuit of a synchronous generator? A voltage source and an impedance associated with it, which is the reactance of the generator, excess synchronous reactance of the generator. So here we convert that to a current source in admittance form. So current source in parallel with admittance, current source in parallel with admittance or impedance, we represent this in the admittance model. Okay. So what was the impedance in this case? J1. So 1 by J1 is minus J1, right? So this is 1 by J1 because J1 was the impedance. This is 1 by J.8, right? This is 1 by J. What was the value here? This line 0.2. So this is 0.5 J5. Okay. Right? So draw this admittance diagram. That means we are converting all the impedances to admittances. So this is the step 2. Right? Clear? So you will be given with a network with voltage sources and impedances, because that is the transmission line impedance. You convert that to current sources and admittances. Okay, done. Next we are going to write network equations. Simple nodal equations based on Kirchhoff's current law. What is Kirchhoff's current law? Total current entering a particular node is zero, or the total current entering a node must be equal to the total current leaving the node, whether it is phasor form or whether it is algebraic direct form, DC current. Okay. So we have converted the impedances into admittances. Okay. So now what is current? Current is equal to voltage into admittance. Okay. So current is equal to line current 1, 2 is equal to V1 minus V2 divided by Z12 for line 1. Okay, which is connecting node 1 and node 2, or bus 1 and bus 2, or V1 minus V2 into Y1, and this is what we are working on. So the impedance diagram can then be redrawn in terms of admittances and transformations to the current sources, which you have already done. Step 2, step 3, writing the network equations. So you can see this with respect to the diagram. So what is current I1? What is current I1? That is equal to the current that is flowing in this line. I1 is equal to this current plus this current. Right? I1 is equal to this current plus this current. What is this current? This is V1 minus V3 into Y13, V1 minus V2 into Y1. Okay. So Y12 V1 minus V2, Y13 V1 minus V3. Also, there is a connection from this bus to the ground. Okay. So current flowing in this direction. Current flowing in this direction to ground. So 3 currents is equal to I1. Okay. Which is V10, V1 minus 0. That is V1. V1 minus 0 is V1. Reference voltage is 0 into minus J1. So write down. Similarly, you have to find I2. And the third bus there are no current. You saw that no generator in the third bus. So that's why it is 0. Okay, total injected current is 0, which is equal to the current flowing to, this is very apparent. Current injected into bus 1 is equal to the current flowing into ground, current flowing to line 2, current flowing to line 3. Why? Because only line 2 and 3 are connected to bus 1. Right? So if there is no line connected to a particular bus, no current in that, so you do not bother about that. Okay? So did you write this? This is for bus 1, this is for bus 2, this is for bus 3, where there is 0 injected current, no generator. This is for bus 4, where there is 0 injected current, no generator. So if you see here, in bus 4, only connection is between 3 and 4, no ground connection, because there is no generator. So simply 0 is equal to Y34 into V3 minus V4. Okay? Or V4 minus V3. 0 is 0. Okay? Did you write all this? Okay. Now just listen. Don't write anything. Now we can rearrange the equations. We can rearrange the equations and combine the terms like this. See here. We can combine the terms like this. For V1, for V2, for V3. Similarly for other parts. Okay. And we introduce the following admittances. This is very important. We introduce the following admittances. This capital Y11 is known as the self-admittance of bus 1. Okay. We'll see that. Self-admittance of bus 1 is equal to Y12 ground, Y12 and Y13, because bus 1 is connected to bus 2 and 3 only. Clear? Similarly, Y22 is equal to Y20 plus 1 and 2, 3. Why? 2 is connected to 1 and 3 only, not 4. Similarly, Y33 is equal to 3-1 plus 3-2 plus 3-4, because it is connected to 3 buses, no ground. Okay? Y44 is equal to Y34, because there is only one admittance. And these are known as, this is self-admittance, these are known as the mutual admittances, which are simply negative of the transition line admittance. See, Y12, Y21 is equal to simply minus of Y12. What is the small Y12? Anyone? Small Y12, what is the small Y12? What it represents? It simply represents the transition line between 1 and 2. It is the reciprocal of the impedance of that side. Okay? Right? Okay. So now you see here, the left side is the current, the right side is voltage into admittances. Right? Left side is the current, right side is the voltage into admittance. Next, we can write the above equations in the following matrix form. We can write the following equations in the following matrix form. Okay, like this. So write down this. I1, I2, I3, I4 can be written as Y11 V1, Y12 V2, Y13 V3, Y14 V4 and so on. Okay, write down this. So this is the equation in terms of Y-bus matrix. Okay, this is the equation in terms of Y-bus matrix. And for a n-bus system, bus system what was this bus system? 4 buses. So for a n-bus system, it can be written as I bus equal to Y bus into B bus. Okay. So if we have the B bus values and if we know the transmission line parameters, we can develop Y bus and simply calculate the current. Once we calculate the current, we can find the power. Power is equal to V into Y. Then once we calculate the single phase power, we can simply multiply 3 to obtain the 3 phase power, and that is the power. For that, software is available. You did not do it in detail. You will be exposed to the software in your lab. Okay. Experiment number 3 and 4, load flow analysis and fault analysis. 3 is load flow analysis. Okay. Okay. So what is I bus? You can just make an arrow and write this. Vector of injected bus currents. V bus is the bus voltages. Vector of bus voltages. Whereas this Y bus is known as the bus admittance matrix. Y bus is known as the bus admittance matrix. Okay. So that is the topic of today's class. What is bus admittance matrix? Okay. Now we'll see in detail what are the elements. Okay. So now the formula. What is the formula for bus admittance matrix? Suppose in exam it will be a question. You will be given a bus, 4-bus system. Okay. And you will be asked to obtain the bus admittance matrix. If you see the past 2 years of gate questions, you will find at least one question related to Y bus. Okay. Either part of the load flow or directly. Okay. Okay. So write down these formulas. So the self admittance is given as simply summation of all the lines connected, summation of admittances of all the lines connected to the bus. And 0 means the self to ground. Okay. And the mutual admittances are simply the negative of the transmission line admittance. Okay. Write down this formula. I will give you a problem after some time. Write down the formula. These two formulas are very important. One problem will be given. So write down. Did you write? Okay. Only the formulas you write. Mutual admittance, self admittance. Now the question is, why we use Y bus matrix, not Z bus? Why you don't use directly the Z impedance? Why admittance? Now, for a sparsely connected network, for example, suppose you consider a node here, bus here. It is only connected to the nearby bus. If it is a 1000 bus system, a particular bus is connected at most to 2 more buses, not every other bus. Okay. For such type of systems, the Y bus matrix is sparse. That means most of the elements are zero. And this feature makes the matrix inversion process very easier when the elements are zero. So you have a separate mathematical technique for sparsity. Okay. Sparse matrix that is generally taught in the PG classes. Okay. So if someone asks the question, why we use admittance instead of impedance for power flow studies, the answer is because the Y bus matrix is sparse, not the Z bus matrix. Okay. Okay. So inspection of the Y bus reveals that the matrix is symmetric around the leading diagonal. So it is symmetric. You see here. Okay. You did calculate this. This is for this question with all these values. Okay. And using this formula, Using this formula, we are going to obtain this kind of matrix. Okay. Just calculate the first element and cross check. Calculate the first element, which is y11. Y11 means y10 plus y12 plus y13 plus y14. It's a 4 bus system, but there is no connection between 1 and 4, right? No connection, so this is 0. What is y13? You calculated just now. What is y13? Small y13, the admittance. Inverse of the impedance of line 1. This is y13 minus j5. Okay. What is this? y12 minus j2.5. And what is y10? Minus 0. Now add it up. So 5 to 7, 8.5. See? Minus j8.5. So these are the y11, y12, y11, 22, 33, 34. The same admittances. Now these are very easy. For example, you told that y13 is minus j5. So what is y13? 1, 3. So it is simply negative of that. Right? That means y13 is equal to y31 is equal to minus of y1, which is minus j5. So that means it is equal to j5. So you see 1, 3 and 3, 1. This one. These two are here. So similarly, the other limits can be calculated. Okay? Here. Okay. In a typical power system, each bus is connected to only a few nearby buses. Okay. Consequently, most of the off-diagonal elements are 0. Off-diagonal elements are 0. Such a matrix is called a sparse matrix. Okay. And efficient numerical techniques can be applied to compute the inverse. Okay. You know that matrix inversion is a costly computational method. Okay. It's very difficult. Takes time for the computer. The inverse of y bus is called Z-bus matrix, which can be directly built and mostly used for fault calculations. Okay. Y bus cannot be used for fault calculations. Z-bus is used for fault calculations. You will see that.
So we take the negative of the admittance because the direction of the current, like from our perspective, is different.
No, we take the negative of the admittance during this. That was derived from this method derivation. See, that was equation when we wrote. Then only it was derived. Okay. 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 So now we move to the problem. The solution is in the PPT. Don't see the solution. Try to solve it. Let's see how many of you correctly obtain the result of answer. Okay. Don't see the solution. Test yourself. This one. First question. Okay. Solve it now.